Welcome to the second lecture of week 5. In the last lecture, we have seen different types of laminates and we have seen how we denote their sequence through proper notation. Now we will go to the actual mechanics of laminates. So, we will start our discussion with laminate thickness and compliance. So, before we go to the actual mechanics behind laminate thickness and compliance, let us try to understand first of all why it is needed, what is relevance, and we try to understand the relevance with the analogy of simple isotropic structures of simple type which we have seen before. So, in most of the cases when we analyze a structure, we generally depending on the situation, depending on the dimensions of the structures and our goal of analysis, we many a times we reduce the number of dimensions and go from 3 to either 2 or 1 dimensional problems. For example, if we think of just a bar kind of structure, a bar or a beam. So, let us say it is a slender structure and it is fixed at this end. So, let us say it is fixed here and let us suppose that we pull it P and there is no eccentricity of the load and this structure is a slender structure. So, when we try to analyze this, the deformation here, the displacement here that we find is P L by A E, and this A is something which we call as extensional stiffness of the structure, or if there can be some more different loads or complicated variations of the load, or there can be complicated variations of I would say cross section or elastic property throughout the length of the structure along direction x. In that case, we solve this differential equation and this gives us the value of the displacement u at different x position. So, for that this extensional stiffness A E is helpful to us. Now, what is the assumption behind having this kind of quantity called extensional stiffness, which is A E? We assume that the displacement u along the cross section is same. So, displacement u along the thickness and along the cross section is same. So, basically we integrate the elastic modulus E along the cross section and we call it extensional stiffness, and that we can do based on the assumption that there is no variation of our solution u across the cross section. Similarly, if the same structure is under bending, if I put a transverse load over it, so instead of the load being along direction x, say if it is along direction z, say there is a load q along direction z, in that case this should experience deformation along z direction and the end shape would be a bending. So, it will the beam will bend. So, in that case we talk about a bending stiffness or flexural stiffness, which we denote as E I, that means E multiplied by the moment of inertia I. Now, that we can do again based on the assumption that the displacement W along the vertical direction is constant, that means the beam does not contract or extend along the thickness direction, and displacement u along x direction is a linear function of del W by del x. That basically comes from the Euler-Bernoulli beam theory, and based on that we reduce this entire 3 dimensional problem to a 1 dimensional problem, which gives a governing differential equation like this. So, with all these things, what we are doing is we are making some kinematic assumptions, and with those kinematic assumptions we integrate some properties across the thickness sometimes across the width also in these cases, and that helps us get rid of some of the dimensions in the problem. Now, this bar problem can be extended to 2 dimensions. Then we have normal force along x, normal force along y, and shear force in the xy plane, and that becomes a 2 dimensional problem. So, in the properties would be integrated along the thickness only. Similarly, this can be extended to 2 dimension, this beam problem, and that becomes a plate problem. So, there can be bending in both directions as well as twisting can also be there, and they are also integrate the properties along the z direction only. So, in case of laminates, our laminates are also very thin. So, instead of going for full 3 dimension solutions of the deformation, we often go for a 2 dimensionalized version of the problem. Now, to do that, to reduce the model, we need to define similar stiffness terms for the laminates. Now, needless to say, our laminates are made of composites which are anisotropic. So, if we compare with the isotropic problem of plate and with that of, if we compare this anisotropic problem with isotropic plate problem, in case of anisotropic problem, we will see many more number of stiffness constants, and that we have to deal with systematically. So, we will go for that now. So, we will do these all these derivations or all these model reductions based on the classical laminate theory. Now, classical laminate theory has some assumptions. In fact, all these model reductions need some assumptions. So, here the assumption is each ply is homogeneous and orthotropic, and our last few lectures were about this only. So, our second week was devoted to make these plies homogeneous. So, we had different properties of the constituents, but through micromechanical study we are able to come up with equivalent property of the composites. So, based on that we say now that the plies are homogeneous. Then we dealt with anisotropy of the plies, and finally, we got the orthotropic property of the plies. And when some ply is oriented along the xy direction, that means along the analysis axis, we call it specially orthotropic, and when it is not oriented with the axis of analysis, we call it generally orthotropic. Then each ply is very thin. Again, this assumption was needed. Based on that only we reduced the compliance and stiffness relations from 3D to 2D, and then we say that all the displacements and strains are very small. Now, we have seen the definition of strain. For example, epsilon x we define as del u by del x. Now, this kind of definitions use infinitesimal strain assumption. That means, the deformation is very small, and if the deformation is very small, then we can say that the higher order terms of del u by del x like del u by del x square. Similarly, there can be higher order terms of del v by del x, del v by del y, del u by del y. All the derivatives of all the displacement components, they are negligible if this itself is small. So, we assume that the displacements are and strains are small. That means, all the analysis that we do are in linear domain. If the strains are very high, then we need to take full definition of strain, which we do not do in this course. In that case, we have to take all the higher order terms of strain, and then the resulting problem would be a nonlinear problem. We also assume that the bond between the plies are perfect. Let us understand this through this picture. Let us assume that this laminate has 4 layers again. So, this is here we have the bond between layer 1 and layer 2, and if this laminate experiences extension, and then if the bond between these two are not perfect, then what may happen is one layer may slip over another. In that case, the resulting the deformation may look something like this. That means, these plies have discontinuity in the displacement at the region where they are bonded. So, this is not permitted. So, we are assuming that the bonds are perfect. If the bonds are perfect, then the bond strength is so high that this kind of discontinuity or displacements will not come. Then displacement and strain continuous components are continuous throughout the laminate. We have already seen that the displacements have to be continuous if we do not allow this to happen, and not only that, the strains are also continuous. So, if this is experiencing pure extension, the variation of strain with the length would be this. If it is experiencing bending, then variation of strain would look like this qualitatively. That means, the strain also does not jump between two layers, the strain has to be continuous, and later on we will see that if the strain has to be continuous, the stresses have to be discontinuous, and we will see that. And transverse shear strains are negligible. That is very important assumption with respect to the classical laminate theory. That means, this kind of deformation that we are seeing here, that is only due to bending. If it has shear also accounted for, then the same bend shape would have looked like this, but this kind of deformations we are not allowing. So, the entire deformation is due to bending only, and when this happens at this phase, that means at all the cross sections, at this cross sections also, at this cross sections also, here also, two things happens. First of all, the line which was plane before the line which was a straight line before deformation, or if we see this entire plane, this section was a plane section. If we see this section as a section, we see a plane section. So, that plane section remains plane before bending and after bending. So, a deformation like this is not possible. Even with this type of deformation also, I can satisfy this requirement that the displacement and strains are continuous, but that would violate this assumption. So, the plane section which was plane before bending has to be plane after bending also, and not only that, here whatever the angle was, for example, here the angle was 90 degree. So, this angle also has to remain 90 degree because there is no shear. So, these are very important assumptions based on which we will define this entire mechanics of laminate now. Now, let us assume this is our laminate and this is, we define an axis system x, y, z, and let us now consider that we take a small piece out from the laminate. Now, if we see that in an enlarged view, so we have a small piece taken out from the laminate. Now, if this laminate experiences bending and also it can experience in plane deformation also, and the bending would be in two directions. So, bending with respect to y and bending with respect to x. So, when it bends with respect to y direction, the shape can look like this, a bend shape with respect to x direction, y direction can look like this, and with respect to x direction it can bend like this. So, this experience bending with respect to both the directions. So, after bending, the same small piece that we took out would look like this. So, it is a biaxial bending, it is bending with respect to this as well as with respect to the other direction. So, it is a biaxial bending, and then on top of that there can be, or there would be, I would say, extension or contraction, then there can be shear also. So, this angle now would change So, if it was a rectangle in the top view before, now it will look like a parallelogram. So, your final deformation would be a combination of all of this, and there can be twisting also. Now, what we will do is we will study this bend shape, and we will, based on that, we will come up with some kinematic considerations, and with those kinematic considerations we will be able to reduce the problem, I mean from a 3-dimensional problem to a 2-dimensional problem. So, we will be able to integrate many of the properties with respect to z direction, then we would get rid of the z dimension and the problem would reduce to a 2-dimensional problem. So, what we will do now is we will look at this bending with respect to y axis, and we study that shape first. So, if we view this same thing now along y axis, let us view this same piece that we took out from that laminate. So, let us say this is axis x, this is axis y. So, we are viewing axis z. So, we are viewing it along y axis. So, if this part bends, if this piece bends, then a bent shape can look like this. Now, here we can see that at the top initial length was this, and it experienced some reduction in the initial length in the length, that means it experienced some compression. At the bottom initial length was this and it experienced some extension here. So, the bottom part is under tension. Now, so there must be some place somewhere with respect to which there is no tension or no compression. That means, whatever length initially was, that length remains unchanged. Now, let us consider a point here, that means in the arm deformed shape, let us say the point was somewhere here. So, let us assume that the mid line is our z equal to 0 line. So, at a height z from the mid line, we have a point A which is under consideration. So, this is say z at a height z from the mid line, we have a point P, or we have point, and let us say we call it a point P. Now, this point moves to here, moves here. So, that means this point experienced some movement along the x direction, and let us call that movement as u. Now, this movement u can be written as this height z multiplied by this angle theta. So, u we can write as minus z into theta, and then this u is happening due to bending only. So, let us call it u b. So, u b is minus z into theta. Now, the question is, what is this angle theta? To understand that angle theta, let us draw a line here tangent to this deformation line, and let us draw a line parallel to z, parallel to x. Now, this line signifies our displacement along w as a function of x. So, this is this line, we can say our line w as a function of x. Or for a 2-dimensional laminate problem, this is a function of x and y, but here we are studying it for one particular y. So, for this particular case it is a function of x. then this slope of the tangent with respect to x we can call it del w by del x. Now, we are saying our assumption was there is no shear deformation, that means this angle which this angle was 90 degree initially and this 90 degree angle remains preserved. So, this is also 90 degree after deformation. Now, if this angle is 90 degree, then we can easily say that this angle theta and this del w by del x they are same. So, we can say that theta is equal to del w by del x because there is no shear deformation. When there is no shear deformation. So, this can be written as u b as a function of x and y as minus z into del w by del x, and this is a very important kinematic assumption, kinematic result I would say, which comes from this assumption of no shear deformation. Now, this same thing apart from bending, with respect to y. Now, apart from bending, this same thing can experience extension also. Now, apart from bending, this would experience extension also. So, initially if the length was this piece was this, then after extension it would look like this. That means, the entire cross section would have same amount of displacement u 0. So, this u 0 is due to extension. So, this is due to extension. So, we can now say that the total u, so total displacement along x can be written as u as a function of x and y and z as u b plus u 0. So, this also can be written as u 0 minus z into del w by del x. Now, just a correction here accordingly. So, this is a function of x, y as well as z. So, this is a function of x, y as well as z because z is sitting here. Now, accordingly we can write displacement along y also as v means displacement along y as a function of x, y and z, a combination of v b which is a function of x, y and z plus v 0. So, that can be written as v 0 minus z into del w by del y. Now, this comes from the bending with respect to the x axis. So, this quantity comes from bending with respect to y axis and this comes from the bending with respect to x axis. Now, so these are very important kinematic relations using which we will define all the stiffness term for composite laminates. Now, based on that we can write the strain displacement relation The strain displacement relations can be written as, we know that epsilon x is del u by del x. So, this gives me, if we put the definition of u as per the kinematic considerations we had. So, this gives us u is equal to epsilon x is equal to del u 0 by del x minus del 2 w by del x 2. Accordingly, epsilon y becomes del v by del y, and this gives me del v 0 by del y minus z into del 2 w by del y 2, and we have gamma x y, which we also write as epsilon x, and that comes as del u by del y plus del v by del x, and then we can write this as del u 0 by del y plus del v 0 by del x minus 2 z into del 2 w by del x del y. Now, this all we write in a more simplified form as a vector epsilon x, epsilon y, epsilon s as epsilon x 0, epsilon y 0, epsilon s 0 plus z into so these terms, this vector is epsilon u 0 del u 0 by del x, del v 0 by del y and del u 0 by del y plus del v 0 by del x, and this vector contains the negative of the curvature terms. So, del 2 w by del x 2 is nothing but curvature. So, slope of slope with respect to x, and then we have minus del w by del y 2, and here we have minus del 2 by del 2 w by del x del y. So, if we combine them, it looks like this: epsilon 0 plus z into this vector kappa. So, this is our strain displacement relation using which we will look at we will do the further development. Now, before that let us understand these components with little more details. So, if the laminate in the undeformed condition looks like this, then del u 0 by del x, which is in plane strain components. So, del u 0 by del x, del v 0 by del y, del u 0 by del y plus del v 0 by del x, which we have written as epsilon x 0, epsilon y 0, epsilon s 0. So, among them this in plane normal strain components, and this is in plane shear. So, an in plane normal strain means just an extension along x direction. So, if this was the original length, after deformation we get this as the deformed length. So, there is uniform in plane extension. Now, the same thing, or this can be a contraction also. When it is positive we call it extension, when it is negative we call it contraction. The same thing, if it extend or contracts in this direction, we call it, this is the signified by the second component, and then there can be a shear which is signified by the last component. So, there can be shear which is denoted by this change of this angle. So, this is from the last component in plane shear. Now, let us look at those curvature terms. Let us say that this is my direction x and this is direction y. So, this is the result of the first curvature term kappa x. So, that is slope of the slope with respect to y, that means a curvature along x direction. So, double derivative with respect to x direction with negative. Similarly, this is x, this is y. So, this is the result of kappa y. Now, here one thing to note is that in the definition of these terms we have absorbed the negative sign, that is why these curvatures are all negative, and this is the result of last term kappa x. So, this is associated with this is a type of bending deformation and this is a type of twisting deformation. So, these are the significance of all these components that we get, epsilon x 0, epsilon y 0, epsilon s 0 and kappa x, kappa y and kappa s. So, with this I would like to conclude this lecture here. Thank you.